Chapter 8, exponential and logarithmic functions. There's a new word. Looks scary, but it's not, because it's partnered up with exponential. So let's start with that. Looking at this function right here. What type of function is it? You should recognize that as one from grade 11. It's called the exponential function. And the equation specifically for this one is y equals 2 to the power of x. So this is a base 2. So for x, if you subbed in a 3, so when x is 3, we would have a y value of 8, because 2 to the power of 3 is 8. And when we sub in a 1, when x is 1, let's go across the x-axis to 1. When x is 1, 2 to the power of 1 is 2. So that's where these points come from. 2 to the power of x, 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. That's this graph here. And then ones that are a little more complicated are the negative ones. So 2 to the power of negative 1, 2 to the power of negative 1 is actually 1 over 2. Remember, we flipped these. We want to find the inverse equation in exponential form. So the inverse equation, if you remember, you take your original equation, y equals 2 to the power of x, and to find an inverse, you switch the x's and the y's. So let's switch them. Now we have this. The next step would be to isolate y. That's how we do inverses of all the other functions, but how am I going to isolate y when it's an exponent? I can't just divide by 2 and then I'll have an exponent of y hanging up in the middle of nowhere. I can't do that. So how am I going to isolate y? So that is the problem. So let's just leave it there for now. Let's just put a pin in that one and come back to it. The next part of this question I want to do is I want to draw the graph of the inverse. That's this thing here. I want to draw the graph of it by switching the x and y coordinates. Let's do that first. There's several parts to D, but let's do this first. Switching the x and y coordinates. Let's take 2, 4. 2, 4, the coordinate 2, 4 is going to go to 4, 2. Remember, that's how we find inverse coordinates. We just switch them. Oh, that's not a good dot. 0, 1 is going to go to 1 and 0. There's where that inverse is. I have negative 2 and a quarter. That's going to go to 1/4 and negative 2, which is way down, maybe about here. There we go. So those are the points we had so far. If you remember some of the other ones I talked about a minute ago, up here we had, on the original, we would have had the coordinate 3, 8. So that's going to give us 8, 3. So let's put that one on there. There's the 8, 3. So all of these coordinates are just the inverse of what we had. Here's 4, 2. And this one is 1, 0. And down here we've got, that was a quarter and negative 2. Okay, so all we did so far is this first part here. It says draw the graph of the inverse by, switching x and y coordinates. Done. Okay, we did that. Okay, next thing, let's connect our dots. So inverse has to have really this very similar shape of your original function. So when I look at that original red curve, I need my green curve to be similar to that. So I'm going to connect the dots in a curve that looks like that. Let's pretend I'm hitting those dots right there. And down we go. Another important part that we haven't drawn yet is the asymptote. So look right here, this dotted line going across this way. This was a horizontal asymptote, and its equation is y equals 0. So when I switch my x and y values, I'm going to get a vertical asymptote on my inverse, and its equation will be x equals 0. So it's going to come right down through the y-axis like this. So I have an asymptote right here. So now I've got the whole inverse graph drawn. The second part says, is this a function? Is this a function? What do you think? When you look at it, would it pass the vertical line test? Yes, it is a function. And the third part of this question says state the domain and the range of both relations. So let me do the first one in red, the domain and range. So the first one, we'll call that one f at x. That's our first function in red. So our function, its domain is, so I'm going to do set notation here. X is an element of real numbers. And we talked about this way back at the beginning of the unit, that we can use any value for x. So just to remind you what that means, if I look at my original equation here for x, I could sub in whatever I want there, a positive, a negative, a decimal, a fraction, anything. So x is the element of real numbers. Any number will do. Now let's look at the range. Looking at your graph, is range y is an element of real numbers? So is the range y is an element of real numbers? Does it include all real numbers? No, it doesn't, because we've got that asymptote stopping it. So we put such that all of the y values in the function are greater than, not equal to, I'm not going to put that line there. If they're not greater than or equal to, they're just greater than 0 because I have an asymptote there. Now on to our inverse function. Inverse notation looks like this. So this is our inverse. The domain first. Is x still an element of real numbers? When you look at the values here, x is an element of real numbers. Is that the end of the story there? Is x an element of real numbers? No, look at those. I can't, my graph doesn't go on the left-hand quadrants at all. So it's not an element of real numbers. Well, sorry, it is an element of real numbers, but that's not all. We have such that all of the x values that are in play here are all greater than 0. Now, how about the range of the inverse? The range of the inverse, that one is y is an element of real numbers. And of course, if you remember, the domain of the function, this one here, the domain of the function becomes the range of the inverse because you're switching x's and y's. So the range of the original function, this one, is the same as the domain. You just switched x's and y's. So the domain of the function is the range of the inverse, and so on. And last part of the question says state the intervals of increase and decrease. Okay, intervals of increase and decrease, we're going to do them both. Let's start with the red one here. The intervals of increase, so maybe I'll put it down here. 2 to the power of x, that's the red one. 2 to the power of x is always increasing. It's increasing everywhere. So we don't have any intervals of decrease. It's increasing. And how do we write, let's go with, yeah, we already did set notation. Let's go with interval notation. Interval notation. So 2 at x is increasing where? So it's increasing for x values that are from negative infinity to positive infinity. It's increasing for all those x values. It's increasing everywhere. Round brackets because we don't include infinity. Now the other one is 2 to the power of y. That's also increasing everywhere. It's increasing everywhere, but it doesn't exist everywhere. So it's x values, and again, if you look over at the domain, it doesn't exist everywhere. I can't write this time the same thing that I wrote up here because it's not increasing from negative infinity all the way to 0. It doesn't exist there. So it actually starts increasing at 0. But do I put a round bracket at 0 or a square bracket at 0? What's going to go there? Are we including 0 or not? We are not including 0. That should be a round bracket. So 2 to the power of y is increasing from 0 to infinity. So those are some basic characteristics of our inverse function. So the green one now is our inverse of the red one. And why is this important that we talk about the inverse of the exponential function? Because the inverse of the exponential function, this whole light green part, is the logarithmic function. That's how these two are connected. Remember when we were up here, I said, let's switch x and y, and then the next step would be isolate y, and we couldn't isolate y. So the logarithmic function helps us access this exponent here so that we can isolate y. So that's what we're leading up to here. The equation of this new function, that light green one that we drew, is this. So that's the way we write it, so that the y is down here and isolated. And we use this log function to bring it down, and we'll learn a lot more about the theory behind that later. The inverse of the exponential function is written using logarithmic form. So instead of writing it the way we had it there on the other slide, which was x equals 2 to the power of y, and we got kind of stuck there, we use logs to change that around. And again, I'll explain more about that later. The exponential function, you already know that one. That's y equals a to the power of x, where a is any base. So today we've only been talking about a base of 2, but our base could be anything. And the inverse of that will look like this. It's really important you match up the letters. So whatever was the base here, this little subscript is called a base. So the word that we would use for base over here is also, we call it base over here. So this is log base a of x. So that whatever your base was stays a base, it just becomes a little subscript. And that a number I'm talking about, which could be a 2 or anything, for us it's always got to be greater than 0 but not 1. So we're always going to have a number there for a that's not negative. Here is what we just did on the other slide, but drawn in Desmos, and then the asymptotes aren't in there. The graph shows, so the purple one is log base 2 of x, which is exactly what we just did. It includes the point 8, 3. So let's make some sense out of how do we get coordinates out of something that looks like this. This is bizarre looking, right? How do we get a coordinate out of that? Subbing into the equation of the function, so this is an x, this is a y. I put them in down here in the place of the x and the y. It looks like this. So look at what you see here. If log base 2 of 8 equals 3, what do you think log base 2 of 16 is? What do you think log base 2 of 16 is? Do you see a pattern here, how our numbers relate to each other? If log base 2 of 8 is 3, what's log base 2 of 16? And hopefully some of you are shouting at your computers right now the right answer. You know what it is. You're saying it's 4. It is 4. So what we're kind of working out in our head here, if we work backwards, remember 2 is our base, so let me write it as a normal base. 2 to the power of what would be 16? That's what you're trying to figure out here. 2 to the power of what is 16? So in this case, it would be a 4. So the answer is this is equal to a 4. Right here, we had two different forms which are kind of expressing the same thing. We're much more comfortable with exponential form right now. And so a lot of us are going to be converting to exponential form all the time because it makes more sense. It's like how a lot of us still would work with radians instead of degrees. You would go to all the extra effort of converting to degrees instead of radians. I think I said that the wrong way. Yeah, you would convert to degrees instead of radians because you like the degrees more. And you might be doing that for this. A lot of this chapter too, you might say, oh, I'm putting that back in exponential form because I don't understand that new log form. But you'll get there eventually. So here, this is our new log function, and that's how it operates. It's getting at the exponent that we couldn't get at otherwise. What meaning does the expression of log base a x have? What is the meaning of that? Log base a of x is the exponent. That the whole thing is the exponent to which a is raised to yield the value of x. What does that even mean? So remember, if we go back to our original, on the first slide, we had y equals a to the power of x. Then I said, find the inverse, switch x and y. We got x equals a to the power of y. We want to be able to isolate this exponent. We want to be able to get at that exponent, and we do that with the log function. So log base a of x, and if you look on your calculator, you have a log button. that's the way we can bring down, this would all be equal to y. That's the way we figure out what y is equal to. So it's actually working to get the exponent. Well, this will make more sense as we go along. Logs are very confusing at first because it's an opposite operation of everything that we have been doing with exponentials. Example 1. Convert between exponential form and logarithmic form. Okay. Pick purple. Convert. So the first one is 1/5 squared equals 125. Everybody understands that, of course. Everybody knows that makes sense. 1/5 squared equals 1/25. So I'm not asking you to solve for anything or find a value of x. All I want to do is get from here to here. How could I write that in exponential form? Remember that it's all about getting at the exponent. So 2, go back to my pen, 2 is the exponent, and that's equal to log, what's the base? Remember I told you about the base? Whatever the base was originally is what the base is, the subscript base is. So this is a 1/5 is going down here, 1/5, and then the other number you're left with is 1/25. That's what's equal to 2. So remember, we're trying to access the exponent, and we do that by using the other parts and reusing these pieces and rewriting them in the right spot to get at the exponent. Because we have a 2 here, but there's lots of questions where this is going to be the x, and you don't know what that is. And so we need to be able to rewrite it. Next one, so try this one here. So first of all, what's the exponent? The exponent is the 4. And so if you didn't know it was a 4, that would be an x, that would be what we're trying to find. And that's equal to, first you write the word log. Now what's the base? What's the little subscript base? It's the same thing that was the base over here. That's the 3 is the base, and then the only other number you've got is an 81. So log base 3 of 81 is 4. Now let's try it with some variables. If a to the power of x is y, then that means the x, the exponent, is equal to log, in this case the base is an a, and then our y is the input that goes there. For some people it's really helpful to memorize these 2 lines because it always helps you switch easily from one to the other. You just match it up. So now we want to go the other way. This time I'm giving you the log, and I want you to rewrite that in exponential form. So we'll start with, look, if you look at what we just did here, let's start with the base. The base, that's an a. What's the base for this question? The base for this question is a 4. Now what am I going to put up here for the exponent? What goes here? That's the exponent. That's a 1/2. And that's equal to, the only other number I have left is a 2. And this makes sense, right? 4 to the power of 1/2 is 2 because the exponent of 1/2 is the same as the square root. So that makes sense there. Next one, last one for the chart. Maybe press pause, write it down for yourself, and then hit play when you're ready to come back. The base is a 10. 10 is the base. I did it in the wrong, well, yeah, I do it in that order. 10 is the base. 10 to the power of 3 equals 1,000. Of course it does. So that's how we go from logarithmic form to exponential form and back again. Let's go through what all these components are called. I'm not gonna expect you to remember all these different things that I'm gonna go through here, but the first y. When we're in exponential form, that's the output. When we're in exponential form, output means the answer. So that's just the answer. The a, we would always call that the base. And that x up there, that's the input. So that would be your 2 to the power of 5, right? The 5 is the input, is the number you're putting onto your base. Now when we rearrange all of that into logarithmic form, let's see what it looks like. The x is now the output. So the whole point again of the logarithmic form is to get at the exponent. So what was the exponent before was an x. Now we need a way to get at that exponent to bring it down so it's no longer an exponent. So what was the input becomes the output because it's an inverse. And then that little a there is the base, but this time it's the base of the log. And then the y is the input. So the y is part of the question. We're subbing in the part of the question to get the answer or to get the output. And again, you don't need to memorize all those terms. That's fine. It's there to help you understand how we go from an inverse, how we go from an exponential to a log using the inverse, and then where all the pieces fall in that process. Example 2, evaluate log base 2 of 16. All right, here we go. So because most of us right now are thinking, I can't figure that out yet. I need it to be an exponential form. Okay, so let's just make it equal to something. Pick any letter you like or pick a question mark if you want, whatever you want to put there. Let's make it equal to something. And then we're just going to change it to exponential. So we're going to convert it to exponential because that's the stage most of us are at. Converting to exponential is, so this is the base 2. 2 to the power of question mark equals 16. So for some of us, that's a lot easier to figure out than the log form. 2 to the power of what is 16? I think we even did this already. That gives us the value of the question mark is a 4, right? We get the value of the question mark has to be a 4. Actually, let me write it out like this. So 2 to the power of 4 is 16. So that means way up here, the answer to this is actually a 4 because that's what we had for a question mark. So log base 2 of 16 is 4. You're asking what exponent with a base of 2, what exponent, that's the question mark, what exponent with a base of 2 equals 16? Well, let's try it again. We'll make a letter this time. Let's make it equal to x. You can pick whatever letter you want because there's none in the question, so I can pick whatever letter I want. So the first thing I'm going to do is convert to exponential because I'm not ready to recognize this format yet. My brain's not there yet, so I'm going to convert it to exponential. Start with the base. The base is a 3. 3 to the power of what? What's the power here? This is the exponent, right? That's what we're trying to get. 3 to the power of x is equal to, now this is a weird number, but that's what goes here, 7th root of 9. So let's just work with that for a second here. 7th root of 9 is really 9 to the power of 1/7. When our bases don't match, we can't finish the question. So I need the same base. And I always have to go with whatever the lower base is of the two. So between 3 and 9, 3 is the lower number. So I'm going to have to write 9 with a base of 3. So let me erase all this mess. So leave the 3 alone, 3 to the power of x. Now instead of a 9 to the power of 1/7, I want it to be 3 to the power of something. So 3 to the power of what is 9? That's 3 squared. So all I did was change the base so that my bases would match. I have 3 to the power of x equals 3 to the power of, this is a power of a power law. That's going to be 2 times 1/7. That's 2/7. So clearly x is equal to 2/7. That's the only thing it can be. Once your bases match, you can ignore them. You're not deleting them. You're not dividing by 3 or subtracting 3 or anything like that. The bases are still there, but we're just, because they match now, all we really need to do is look at the exponents. So this tells us that x must be 2/7. Okay, one more. If you want to try this one on your own, now's a good time to press pause. Let's make it equal to, how about w? Whatever letter you like, w. Rewriting an exponential form. Our base is a 2. 2 to the power of w equals the, now we're putting down what is the input, which is 1/64. So I need the same base. And I'm not looking at the fact that 1/64 is a fraction. I'm actually just looking at the 64 itself. So when I compare a 2 and a 64, the lower number is the 2. So I'm going to keep the 2 alone. And I'm actually going to write 64 to the negative 1 because it's much easier to look at it as a whole number than as a fraction. Okay, now we need our bases to match. So 64 is 2 to the power of what? 2 to the power of what is 64? What am I going to put in that little box? Use your calculator if you need to, but the bases of 2, you should know some of those pretty quickly. It's 2 to the power of 6. Over here, I've got a power of a power law, which means I multiply those two. 2 to the power of w equals 2 to the power of negative 6. So now I see what w is. W is negative 6. So my answer to this question is negative 6. That's the answer. Log base 2 of 64 is negative 6. Next, example 3. This is our last example. Write the coordinates of the 5 points that have these y values for that logarithmic function. What are they talking about here? These are y values. These are all y values. And here's a y. So the first thing I'm going to do is replace first the negative 2 is going to go there. I'm not going to solve it yet. I'm just going to lay out the question for you. So the first one is a negative 2. The next one we have to do is a negative 1. I just put a line here to divide them up. So we have to use all of these values here in turn, one and the other, and we're going to find all of those answers here. So if we were in class, I would have different people come up to the board and do their work, or you'd work in partners, but that's not the case. So let's start with the first one. Negative 2 equals log base 5 of x. So we're still converting to exponential, some of us, because that's just, and that's fine. Today, everything can go into exponential form, even tomorrow, doesn't matter. Let's rewrite that. What's the base here? The base is a 5. The exponent will be a negative 2, and that needs to equal x. So that's a lot easier to look at and to solve, but you're going to get there eventually. You're going to look at this form and say, oh, that's just 5 to the power of negative 2. I don't need to write it out. I can just do that little mental thing there. But until we get there, let's do the steps. This is 1 over 5 to the positive 2 equals x. And that's going to be 1 over 25. So the coordinate, remember the question said write the coordinates? So this coordinate, the x value is 1 over 25. And the y value that we put in here originally is a negative 2. So that's a coordinate on this graph right here. When we need to graph that, that will be the first coordinate we can put on our graph, which is pretty hard to do 1 over 25. Next one, let's do the same thing. 5 to the power of negative 1 equals x. That's 1/5 equals x. So the coordinate is 1/5 is my x value, and my y value this time was a negative 1. I'm going to graph that one. Next one, 5 to the power of 0 equals x. What is 5 to the power of 0? Is it 0? No, it's 1. My x value is a 1, and my y value was a 0. Next one, 5 to the power of 1 this time. 5 to the power of 1 is x, so that's just a 5. This coordinate is 5, 1. And then our last one, the base is a 5, the exponent is a 2. That will give me x. 25 is x. So my coordinate is 25, 2. So on the next slide you're going to see the graph of this function. I already graphed it in Desmos. There we go. That's log base 5 of x. That's what the graph looks like, and those points are the coordinates that we came up with. Now, Desmos doesn't put the asymptotes in. We're going to talk more about asymptotes later, but we would have an asymptote running right down the y-axis right here. And that's it. That's the end of your introduction to the logarithmic function.